My name is Susanna Kohler. I'm the AAS press officer, and I'm happy to welcome you to this press conference on Tuesday afternoon at 2:15 p.m. on the 6th of January, 2026 in Phoenix, Arizona, at the 247th meeting of the American Astronomical Society. This is the Milky Way and stellar explosions. We are very excited to have all of you here today and to have our presenters here today talking to us about this subject. I am joined by my co-hosts here, Carrie Hensley, Deputy AAS Press Officer, and Lexi Galt, the AAS Media Fellow, who will be helping to monitor things online and also take the mic around in the room today. And in terms of the press conferences we've had so far in this meeting, we've got the press kit updated, so all of the press releases, the slides from the presenters that we have, and the briefing videos are all in the press kit online. You can find this in the press section of the meeting website, and you can also find it linked out from the Slack. The press conferences channel in the Slack has all of these as well. And we will have press releases. I didn't actually ask how many of you have press releases. All of you, great. We will have press releases from all three presenters from this session linked out of there as well by the end of the day. So with all of that said, if anybody here has not yet been to a press conference at the AAS, just a quick rundown of what this looks like. We ask first off that everybody silences their cell phones or anything else that makes noise. Note that we are live streaming this to YouTube and recording it. And the way we'll do this is each of our presenters will go in turn after a brief introduction from me, introducing them and their presentation titles. Then they will go in turn and do their presentations, and then we'll move to a joint Q&A session for everyone. At that point, we'll have a handheld mic that we can walk around the room. So if you have a question, you can just raise your hand, and Lexi will bring the mic around. And then we ask that you identify yourself and your affiliation and who your question is for. And for those of you who are watching online, if you could do the same, if you're watching via Zoom, you can queue up your questions via the Q&A box. And we ask that you put in your name and affiliation and who your question is for there as well. And then Carrie will be able to read those out during the Q&A session. So with all of that said, we will go ahead and get started. As I said, this is the Milky Way and stellar explosions. And leading us off, we're going to have Steve DiKerby from Michigan State University discussing resolving iron doublets for galactic center molecular clouds with, I actually don't even know how to pronounce, is it XRISM? That's, we're going with XRISM. Okay, Merry Christmas. Yes, with XRISM. Then Jessye Gassel from George Mason University and NASA Goddard Space Flight Center will present continued monitoring with Chandra of Kepler's supernova remnant for over 25 years. And lastly, Sumit Sarbadhicary from Johns Hopkins University will present Where Do Stars Explode in the Interstellar Medium? We've got three presenters this time, so we should have plenty of time for questions afterwards, and we may even end early as opposed to late. So let me go ahead and get the screen sharing set up again. And Steve can lead us off.
Thank you. I appreciate the introduction, and thank you for having me here. Let's see. There we go. Should be seeing slides okay. Like you said, I'm Steve DiKerby. I'm a postdoc at Michigan State University. And today I'll be talking about some new results we've just coming out in the Astrophysical Journal Letters and on arXiv today, using XRISM to look at galactic center molecular clouds. These results, like I said, on XRISM on arXiv today wouldn't be possible without the collaborators I've listed here. And if you want to learn more, my contact info is at the bottom of the slide. So let's start with just a little bit of background before we get to the new science that we're doing. When we look in towards the galactic center, we're seeing the most crowded, chaotic environment in our galaxy. Hundreds of millions of stars are all packed in to the bulge of our galaxy, just a few hundred parsecs across. Besides all those stars, the galactic center also has a variety of exotic objects that are unique, studied in high energy X-ray and gamma ray light. Most famously, that includes Sagittarius A star, a supermassive black hole at the center of our galaxy, but also a collection of molecular clouds that make up the galactic center molecular zone. Despite being only a few hundred parsecs across, this molecular zone contains about 5 to 10% of the total molecular gas in our Milky Way galaxy. It's a very dense environment. When we look at these clouds in X-rays, their X-ray radiation is dominated by a very particular type of X-ray photon. It's an iron K alpha photon at 6.4 kiloelectron volts. The atomic physics is something beyond the scope of this presentation. Suffice to say, this is a particular transition in an iron atom. And when we use this particular type of X-ray photon, we can learn a lot about the galactic center. We can use it to explore the history of Sagittarius A star, how it's gotten brighter and dimmer over the past 1,000 years. We can use it to measure the ambient cosmic ray environment in the galactic center. And we can also use it to measure the 3D arrangement of these molecular clouds around Sagittarius A star. Now, the galactic center molecular zone has been studied extensively in the past with other X-ray telescopes, Chandra, XMM Newton, and you see here on this slide in NuSTAR and high-energy X-rays. But my collaborators and I, for the first time, have used a new X-ray telescope, XRISM, to do new science in the galactic center. XRISM is an X-ray telescope that was launched in 2023. It's a joint American and Japanese mission. Its superpower, what makes it special or different compared to other X-ray telescopes, is its ability to measure the energy of an X-ray photon with unprecedented precision. It can constrain the energy of a photon 50 times better than other X-ray telescopes. This allows for remarkable new science. An analogy I like to use is that other X-ray telescopes can only see the sky in a few discrete colors, only a dozen, but XRISM can see a whole rainbow of thousands of continuous colors. This is valuable for looking at the iron K alpha photons I mentioned previously. Because they're only emitted at one particular energy, XRISM, in blue in the plot on the right, can resolve that spike of emission with great spectral energy resolution, whereas other telescopes in red just see kind of a Gaussian blob of blurred photons. So what do we see when we look at a galactic center molecular cloud in XRISM? My collaborators and I looked at the cloud G0.11, highlighted on the right here. The spectrum we found is on the left. As we zoom into the iron K alpha line, which dominates the spectrum, you see XRISM's unique capabilities. For the first time, this line is resolved into a doublet, two separate lines separated by 13 electron volts. This is only possible because of XRISM's energy resolution. This unlocks entirely new ways of analyzing X-ray data. First, we can measure the flux in each of these two components, and we find an exact 2-to-1 flux ratio, as predicted by quantum mechanics. We can also measure the redshift of these lines with unprecedented precision. We constrain the redshift of the cloud, how fast it's moving towards and away from us, blue shifting or red shifting the photons it emits, to 10 kilometers per second precision. That's the same precision achieved by radio and infrared observations of the galactic center. This is simply unexplored terrain in X-ray astronomy. Such precision has never been achieved by an X-ray telescope before. And finally, we can measure the width of these lines, measuring it to about 3 electron volts. That is very close to the quantum mechanical minimum of the iron K alpha transition, suggesting that these clouds are very cool systems. There aren't any broadening effects taking place. We can compare the width of these lines to part per million laboratory measurements here on Earth, unlocking an entirely new way of doing laboratory astrophysics and connecting what we explore here on Earth to systems on the other side of the galaxy. So just analyzing this spectrum, this data we got from XRISM, a new telescope, we had to develop entirely new analysis techniques, which we're excited to use in the future. But what does this tell us about the galactic center? I mentioned how these clouds emit a lot of X-rays at this iron K alpha transition, but why is that the case? Why do they emit so many X-rays? There are two leading hypotheses. The first is the X-ray reflection model. In this hypothesis, an external source of X-rays, perhaps Sagittarius A star, the supermassive black hole, illuminates the molecular clouds with high energy photons. These photons are reprocessed as they interact with iron atoms, eventually producing the 6.4 keV emission that we see in XRISM. In the alternative cosmic ray excitation model, these galactic center molecular clouds are submerged in a high-energy bath of particles, protons, electrons, and ions. And as these high-energy particles bombard iron atoms in the cloud, they excite electrons, which leads to the X-ray emission that we see. These two competing models have been tested in the past with other X-ray telescopes in terms of time variability, how the clouds change in brightness over time, and polarization, how the light coming from the clouds is polarized. But for the first time with XRISM, we can test these two models in an entirely new way by looking for secondary spectral features that have previously been entirely unobservable. So when we look at the XRISM spectrum around the 6.4 keV line, these two models make a couple different predictions for what we should see. Above the primary 6.4 keV peak, the cosmic ray excitation model suggests that there should be some secondary satellite lines. You can see them in blue on the right here. These lines are produced when a single particle excites multiple electrons in an iron atom, but clearly we don't see them in our data in black. We know we should be sensitive to them if they are present, but we don't see them. This places a very strong constraint on the cosmic ray excitation model and suggests the majority of the iron K alpha emission we see is a product of external X-ray reflection from some external X-ray source. Next, in the X-ray reflection model, some photons can be scattered multiple times by ambient particles as they leave the cloud. This produces a hump of emission below the main primary peaks called the Compton shoulder. We know XRISM should be sensitive to this as well because our Japanese collaborators, Nobukawa et al., have an upcoming paper where they investigate this emission, but we don't see that in our data as well. This lets us make direct physical conclusions about the properties of this cloud because it suggests that an individual X-ray photon doesn't scatter more than once as it leaves the cloud. That's called being optically thin. So in the X-ray reflection model, we can make these new physical predictions because of XRISM's energy resolution. These secondary features wouldn't be visible in other X-ray telescopes even if they were present, because those other telescopes don't have the energy resolution needed to push the background continuum down and determine and find these features here. So let's take a step back and look at the big picture. To analyze this new XRISM data at these very, very narrow emission lines, we had to develop entirely new X-ray analysis techniques. We got a tight redshift constraint with X-rays, which previously has simply been impossible to do. We can compare our X-ray profiles that we see in these molecular clouds to laboratory measurements here on Earth because of XRISM's spectral resolution. And finally, we can use that resolution to search for very subtle secondary features, and this allows us to make physical conclusions about the cloud and the galactic center environment. Specifically, our findings support the X-ray reflection model for why these clouds are illuminated. Some external source of high energy light, probably Sagittarius star, in the past illuminated the cloud with X-rays, which we see reflected by the iron atoms therein. And when we use this model, we come to the conclusion that Sagittarius star in the past used to be much, much brighter than it is today in X-rays. This is just one piece of a puzzle to understanding the history of the galactic center, the environment of these molecular clouds, and the new capabilities of the XRISM telescope. So I'd of course like to thank all my collaborators for their help and the XRISM team for helping make this analysis possible. Thank you very much.
Hi, everyone. My name is Jessye Gassel. See, is this coming up? There we go. I'm a fourth-year grad student at George Mason University, and I do research with Brian Williams from Goddard Space Flight Center. And today I'm here to update you on Kepler's supernova remnant. So Johannes Kepler observed this new star, as he called it, in October 1604. But we now know that it was a supernova and have named it after him. And it is, you see in the picture on the right, it's a nice little drawing of the sky. So this is Kepler's original drawing of the constellation Ophiuchus, and he placed the new star in the foot denoted with the N. If you can see it, I put a circle around it to help. But this is the last definitively observed supernova in the Milky Way. And the Chandra X-ray Observatory has observed this object repeatedly since 2000, so about a quarter of a century. And that quarter of a century is only about 6% of the remnant's lifetime. So the Chandra X-ray Observatory, fantastic. So we want to use X-rays, look at the X-rays, because they're the best way to observe young supernova remnants because the particles are so hot, up to almost 10 million degrees. And Kepler supernova remnant is the result of a type 1a supernova, which is when a white dwarf explodes in a binary system, and it's located about 17,000 light years from Earth. And Chandra can make exquisite images of the debris and the shockwave and how they expand with time. And it's important that we understand these events because it helps cosmologists measure the expansion of the universe. But there's still a lot unknown about these type 1a explosions and how they happen. Okay, so here is an updated movie. It's going to loop around and I'll just tell you about it. So we start at 2000, which is the first observation, and then the most recent observation ends it in about June 2025. And I would just like to say that we are not the first to do these proper motion measurements. It has been done before over a 6-year window and a 14-year window, as well as in other wavelengths like the optical. And this is the longest spanning movie that Chandra has ever produced. So that makes it the most accurate measurements that we have of this object so far. So just want to zoom in on parts of it so you can get a better look at how it's expanding. Over here, this is about the 7 o'clock zone. And there's this nice bright filament that we see, and that is what we are measuring. And I'd like to remind everyone about that, like 6% of its lifetime. So that's about half a light year that it's traveled, or 3 trillion miles. And then if we look over at another part of the remnant, there's another bright filament, and it's another good look at what's going on. So this is quite an unusual type 1a supernova. So previous observations imply a very high density of gas that the shockwave is running into, with different densities in different parts. And that's what makes it so unique. It's kind of rare to see this in a type 1a supernova. And this interaction with the dense material is likely from the progenitor system before the star exploded, and it's running into that material, which we call the circumstellar medium. And with expansion measurements over many years, we can directly probe how the velocity of the shockwave depends on the density of the surrounding medium. So measuring the velocity tells us about the environment in which the star exploded, and knowing the environment informs us on the stellar system. So we find direct evidence of higher density in the north of the remnant, and we are getting velocities at 4 million miles per hour. And there are lower densities in the south, where we are getting a velocity measurement of about 14 million miles per hour. And these velocities confirm previous works that have looked into the density surrounding the remnant. So I just want to finish up with just reminding everyone, this is the longest movie Chandra has ever made. It is quite a feat. And we need to keep monitoring this supernova remnant, and we need to use high resolution X-ray observations. So got to keep using Chandra. If you would like to see the full press release from the Chandra press office, go ahead and scan this QR code, and please feel free to contact me if you have any questions.
All right. Good afternoon, everyone. My name is Sumit Sarbadhicary. I'm a assistant research scientist at Johns Hopkins University. My email is down here under the title. And today I will tell you about my results on where do stars explode in the interstellar medium, which has significant implications for galaxy evolution. So first of all, why do we care about where stars explode? Supernovae, or which is what we call stellar explosions, are the main drivers of galaxy evolution. And I like to illustrate this always in my talks with the starburst galaxy M82, which is shown over here. Right at the center, there's a whole bunch of supernovae that are constantly exploding, probably like once every 10 years or so. And there's actually one supernova that was seen about 12 years ago, 2014J, which you see in the top left here. This was one of the closest supernovae of our lifetimes. And so there are tons of these supernovae that are happening in this galaxy. And the energy and the heat and the momentum generated drives a whole bunch of important processes like outflows, which you see in this picture here in this brown and maroon things that are kind of emanating out of the galaxy. And then a bunch of other things like hot gas, which you saw in the X-ray images of Kepler. There's turbulence, which you can see in line images, cosmic rays, dust, atom molecule, the production and destruction of these things, the triggering and seizing of star formation. All of these things are regulated by supernovae explosions. They are literally the DNA of galaxies, kind of like just how our DNA determines how we look and how we behave and the things we like and don't like. The supernovae basically dictate what galaxies look like and how they evolve over time. And on that note, I kind of like to show this XKCD cartoon quite often. And this is not an exaggeration. The entire field of galaxy evolution, whether you're studying black holes or whether you're studying star formation or whether you're studying the circumgalactic medium, all of that really depends on how well we understand the physics of supernovae and stars, and if we are implementing them correctly in our simulations. So this is really important to understand. And one of the things about supernovae that we are trying to figure out, there's a whole bunch of things, but one thing that particularly caught my eye was the understanding of what is the environment where stars are exploding, the gas environment. And this is kind of a non-trivial question because we know that stars are born in dense molecular clouds, right? These are the nurseries in which stars are born. And typically stars are short-lived, especially the most massive stars that actually impact galaxy evolution. But at the same time, stars also move from their locations. Stars produce ionizing photons, which can destroy molecules. So the balance of these processes, exactly how that affects the environment where the star finally explodes, is something that we haven't quite figured out yet. And there are a lot of people that are trying to study this in different ways. But in the meantime, the people who study galaxy evolution are finding some concerning things. So this is illustrated by this simulation. This is by a German collaboration called SILK. And this is a simulation of the interstellar medium of a galaxy kind of viewed edge on. And I'm showing the same simulation on the left and the right. They're the exact same thing, same initial conditions. The only thing that is changing is the way the stars are located with respect to the gas clouds, okay? So on the left, the stars in the simulation are exploding randomly with respect to gas clouds. And then on the right, the stars are exploding right inside of the gas cloud where they're born. And you can see that the interstellar medium, which is shown in density and temperature, you can see that the interstellar medium on the left and the right are completely different. Okay, on the left, you have this very thick interstellar medium with lots of hot gas, which you can see in red, and then you have lots of really densely compressed molecular clouds, which have been compressed by the supernova shocks. And then that's completely different on the right, all right? It's a very thin-looking gas disk. There's basically no hot gas at all. And the molecular clouds, which are in blue, are kind of these like spaghettified pasta-looking clouds, which we don't actually see in real life. So people are trying to figure this out, but in the meantime, I was thinking that, I'm an observer, and we are in a really nice era of imaging of the interstellar medium with things like the Very Large Array and ALMA and JWST, we're in a really good place to just make a census of where stars are exploding in nearby galaxies. And that's the subject of this project, which is, I would say, the first detailed census of where stars are exploding in the interstellar medium of galaxies. And so to do this, I started with one of our nearest galaxies, M33, which is more commonly known as Triangulum. And this image right here shows what I call future supernovae, i.e. red supergiants and Wolf-Rayet stars. So the reason I'm calling them future supernovae is because they're still stars right now, okay, but they're evolved stars in the sense that they have finished burning hydrogen in their cores and they're done with about 90% of their life. And so they're going to have only about 500,000 years to 1,000,000 years left before they explode. And because of that, their current locations are basically where they're going to explode in the next 500,000 to 1,000,000 years. So they're a really good way to approximate where stars are going to explode. And the thing is, in our local group galaxy, there's not a whole lot of supernova. As you heard, the last big supernova in the Milky Way was Kepler, which was like 500 years ago. And so you're not going to get a whole lot of supernova explosions, but you can get lots and lots of future supernovae. And then the other great thing is that red supergiants and Wolf-Rayets, they're kind of different mass brackets. The red supergiants are roughly 8 to 30 times the mass of the sun. The Wolf-Rayets are the most massive stars in the galaxy, more than 30 solar masses. So this was a survey done by Philip Massey and Catherine Nugent using Kitt Peak right here in Arizona. So I took that catalog and we put that in what I would consider is the most detailed map of cold gas in the Triangulum galaxy. And this is being done as part of the local group L-band survey, which is using the Very Large Array and ALMA, the Atacama Large Millimeter Array, to make maps, the most detailed maps of atomic and molecular hydrogen in these galaxies. So basically, I just take these locations of stars, I put them on the gas maps, and I just record that. So that leads to this result, which is basically the cumulative histogram of densities at the locations of our Wolf-Rayet stars and at the locations of our red supergiants. Okay, so I'm going to break this down for you real quick. The RSG and Wolf-Rayet is basically acronym for red supergiants and Wolf-Rayets. So the first thing that we noticed from this measurement is that more massive stars are more likely to explode in dense gas. And this is kind of shown in this little cutout here of NGC 595, which is one of the most active star-forming regions in M33. And you can see, sorry about that, you can see in this cutout that the most massive stars, the Wolf-Rayets, which are colored in cyan, are near the center of this green contour, which is a big molecular cloud. Okay, so this is where the gas density is the highest and the most massive stars are closest to that, whereas the lower mass stars, the red supergiants, which are colored in red, are much farther out. Okay, so these stars are going to be exploding probably very close to this dense region, whereas the lower mass stars will not. However, we also see that there are a lot of massive stars, a lot of Wolf-Rayet stars, at least 44% and up to 72% for red supergiants, that are not going to be exploding in any dense gas at all. Okay, and that brings us back to that picture of stars exploding randomly and driving a lot of hot gas, hot winds, which has a significant impact on how the interstellar medium produces stars. And again, a visual picturization of this, here's another region of M33 where you have these Wolf-Rayet stars that are kind of in the middle of nowhere, right? You have these green contours showing the molecular clouds, but then these Wolf-Rayet stars are just by themselves. So what is the significance of this? This is the first time that we have actually measured what fraction of stars that are exploding as supernovae are correlated with dense gas clouds. This is an important input parameter for galaxy simulations. And we're able to do this because of these high-resolution imaging facilities like the Very Large Array, like ALMA, and then very soon we're going to have the Square Kilometer Array, the next generation VLA, and so this is a significant science case for those. And also we are entering, this era of Rubin, Roman, Euclid, which are going to be making images of red supergiants and evolved massive stars very easily in vast swaths of our nearby galaxy populations. The finding, which is significant, is that there are a significant number of stars that explode outside of dense molecular clouds, and that is really how we end up driving winds. We end up preventing star-forming cold gas from condensing into future generations of stars. But at the same time, there are stars that also explode inside or near dense gas clouds. It's not 0%, which is kind of what was suggested by certain simulations, but it turns out that there is a non-zero fraction of stars that does explode near dense gas clouds. And the breakthrough here is that we're actually able to put a number on what these fractions of stars inside and outside of clouds are. And as I mentioned, that this is very important for numerical simulations because these simulations are basically how we study, how we understand galaxy evolution. These simulations, they compress billions of years of galaxy evolution into the timescale of a PhD or the timescale of a postdoc. And unfortunately, these simulations are only as good as the physics you put in them. So having observations like these are really useful to kind of check the nuts and bolts of these simulations so we can make more accurate predictions of how galaxies evolve. So with that, I will leave my email up here and happy to take questions later. Thank you.
Thank you so much to all of you. So let us go ahead and go to questions. So we've got a mic in the room. Again, feel free to raise your hand for questions. And when the mic comes to you, if you could identify yourself and your affiliation and who your question is for, that would be great. And for those of you on Zoom, you can queue them up in the Q&A box. Let's start over here with Kohler.
I'm Govert Schilling, freelance writer from the Netherlands. Actually, I have a question for each of you, if that's possible. For Stefan, I was wondering if the reflection model tells you that there has been an explosion at Sagittarius A star. Do we know how long ago that was?
That's an excellent question. Thank you. So using the different molecular clouds in the galactic center, because they're each a different distance from Sag A star, it takes a different amount of time for a photon from a Sag A star outburst to travel to the cloud, then be reflected back towards us. So each cloud tells us a different, gives us a different view into the past. The cloud that we studied, G0.11, is about 100 light years away from Sag A star. So it's showing the supermassive black hole as it appeared a century ago. And using the reflection model, we can measure the required luminosity, how bright Sag A star would have to be to illuminate the cloud. We find it would have to be 1,000 to 10,000 times brighter than it is today, than we see it, which is really a remarkable suggestion that Sag A star has had a great degree of variability in its high energy emission, even in the recent past.
Okay, thank you. And for Jessye, I was wondering, you were mentioning the factor of 3 in velocity difference between the northern part and the southern part of the supernova remnants, but still these edges are more or less the same distance from the center of the nebula. Does that mean that the deceleration started in only recently? And do we know about the expansion history of different parts of the nebula?
Yeah, so Kepler supernova remnant is pretty spherical, but since we know that there's the different densities surrounding it, we wouldn't expect it to expand spherically. But what's happening is even though there are different densities that the blast wave are running into, the location of where the star exploded is actually moving instead of having a warped shape at the edges.
Okay, so the slower moving northern edge is actually closer to the original center of the explosion. That's what you're saying?
Yeah.
Okay. And finally, for Sumit, I was wondering if these Wolf-Rayet stars are also being observed outside the molecular clouds. Given their short lifetimes, does it mean they have a high velocity because they're probably born in the molecular clouds?
Yeah, I realized I kind of glossed over that point, but that's a great question. The thing that I think is happening, given the number of them that are outside of molecular clouds, but also associated with star formation, I think what's happening is that these wolf-rayettes produce very powerful ionizing radiation. And so what that does is that it literally destroys the clouds before the wolf-rayette will explode. But there may be like a small fraction of them that may be traveling really fast, and they might end up escaping.
Ethan?
This is Ethan Siegel from Starts with a Bang. I only have one question. I hope that's okay. This is for Jessye about the Kepler supernova remnant. You showed some really interesting variations in velocity observed from the blast wave of the ejecta that are expanding. And I was wondering if those velocity variations can be translated into actual estimates for the gas density in the medium surrounding the supernova estimates. And if so, do you have those quantitative estimates?
So it is possible, but we don't have any of those numbers quite yet. This is very preliminary data, and there has been previous works that have used the proper motion measurements to try and get a measurement of the densities in the different areas.
Hi, my name is Julia Falcone, and I'm a graduate student from Georgia State University. Sorry, I'm not press. I have a question for Sumit. I was wondering if you are planning or have thought about performing a metallicity study on M33, because if these supernovae are occurring throughout the interstellar medium, I would assume there would be a more uniform metallicity gradient in the gas compared to if the supernovae are limited to these clouds, you'd see very different metallicities within the clouds compared to outside the clouds. Have you performed any sort of analysis on the metallicity?
Yeah, that's a really good question. The answer is not yet. But yeah, it is something that we would like to do. The problem is that, not problem actually, the challenge is that it's hard to measure the metallicity unless you have ionized gas, because that's the only way in which we get like line emission, and that's how we get metallicity. At least that's how we can do that at the moment. But yes, there are lots of supernovae happening in ionized gas. And there are projects like Sloan Digital Sky Survey and CITEL that are planning to kind of map out the emission lines in these galaxies. And so if you technically just put these red supergiants, wolf-rayette stars in those maps, you get a measurement of metallicity. And you can do the same thing that I did here. So haven't done that yet, but excellent suggestion.
Let's take if there are questions online.
All right, the first question here is to Stephen. This is from Bill Waller at the Galactic Inquirer. Given your resolved doublet emission from the galactic center molecular zone, what is the corresponding kinematic interpretation?
Sure, that's a good question. So we can constrain the kinematics of these clouds because with such high energy resolution in XRISM, and because these lines are so clean and precise, we can measure the redshift, the bulk movement of the cloud, as well as the dynamics of the matter in the cloud itself. So the redshift tells us the bulk motion of the cloud. We measure the redshift at 50 kilometers per second with respect to the local standard of rest, which is the average motion around the solar neighborhood. We can use that precise redshift to link up with radio and infrared maps of the galactic center and say, because these radio measurements, these X-ray measurements have the same redshift, they're probably coming from the same cloud. And then the line width of the profile of the iron K alpha line itself, we can use that to determine properties of the material within the cloud. Because the lines are so very narrow, so close to the quantum mechanical minimum, we can constrain the temperature of the cloud. And in agreement with radio findings, we find these clouds are very cool, only a few tens of degrees Kelvin. Those are the dynamical measurements we can do using XRISM.
Great, thank you. I have one more here, also from Bill Waller at the Galactic Inquirer. This one's for Sumit. have you examined the correspondence between the red supergiants and Wolf-Rayet stars in M33 with respect to the mid-infrared emission from polycyclic aromatic hydrocarbons from JWST? That would that would provide another well-resolved check on the star versus gas position.
Yeah, again, that's an excellent suggestion. We have not done that yet, but we are working. So myself, Eric Rozalowski, Eric Kosh, we are trying to. Actually, we're engaged in a JWST survey of M33, where we do have some of these bands that cover polycyclic aromatic hydrocarbons. The problem is that they don't cover the entire footprint of M33 that I showed here, but we are trying to get that footprint. And when we get that, it would be an absolutely amazing result, because these maps that I showed, these are at 50 parsec resolution. And with JWST, we can get that down to 1 parsec, so like a factor of 50. Yeah, that is going to answer a lot of interesting questions. Like these molecular clouds that we see, are they actually like a big ball of cloud, or is that like a cavity that we see in a higher resolution image? So I'm really looking forward to that, yes.
Lexi.
Hello, I'm Lexi Galt with the AAS. I had a question for Stephen, and this might be naive, but I was wondering how the molecular gas clouds can survive when they're being bombarded with a bunch of X-rays. Because to me, I would like nominally assume that, any X-ray emission from Sagittarius A star would heat up all of these molecular clouds around it. So
That's a really great question that touches on a lot of big questions we're currently trying to understand about the relationship between supermassive black holes and the material around them. There's definitely been studies looking at how supermassive black holes, specifically in AGN, can reshape the galaxy around them. Even though, again, I mentioned that our results suggest that Sag A star was thousands of times more luminous than it is today, that doesn't put it anywhere near the luminosity of an AGN. There's a luminosity measure called an Eddington limit, which is roughly how much energy you can get out of a black hole through radiative processes. AGN are about at that limit. Sag A star today is at about 1/millionth of that limit. So even with this amplified emission we see, it'd only be about 1,000th of the Eddington limit, still nowhere near the energy you need to dramatically and immediately reshape the galaxy. So our results have exciting implications for the galactic center, yes, but you need a lot more juice out of Sag A star if it's going to reshape its environment in an immediate way over short time scales.
thank you.
Carrie. Hi, I'm Carrie Hensley from the AAS. I have a question for Jessye. I love this video that you've shown. Sorry, not this video. This video that you've shown of Kepler supernova remnant. How cool would it have been to have Chandra for the other 94% of its lifetime? I'm just curious if there are other supernova remnants that were observed early enough in Chandra's lifetime that we could create similar videos, or is this really just an example where it's young enough and close enough to be able to actually see the expansion?
So Kepler supernova remnant is kind of that special case because it is pretty close to us. There are other supernova remnants that I have looked at and plan to look at, like Tycho or Gassel, but we just don't have as recent of an observation. So Tycho's most recent is 2021, and I can't quite think of Gassel off the top of my head, but we just need to be able to get the observations to make more movies like this.
Can I ask a follow-up on that? Susanna Kohler, AAS. What are the limitations on Chandra in terms of lifetime? I don't even know.
Of the instrument?
Of the instrument, yeah. Yeah.
So,
like, will we be able to keep extending this movie out?
so hopefully at least we could get maybe another 10 years, but, Chandra wasn't built to last forever, unfortunately.
Mhm.
But there are other high resolution telescopes that are in the works,
Mhm.
such as like Axis.
Right, okay.
Hello, Daniel Perea with Griffith Observatory. I have a bit of a sillier question for Jessye. How accurate would it be for you to say that you could possibly repurpose the XKCD comic that Sumit had in his presentation and repurpose it to showcase Chandra's impact to the field of X-ray astronomy?
I mean,
I can give you the template.
yeah. Yeah, I'll get back to you on that. That'll be a separate press release.
Any further questions in the room? Yes.
Julia Falcone again. Hi, I'll ask another one, this time for Steve. With the improved resolution of XRISM, do you think that any similar studies of the iron K alpha doublet could be performed on any other nearby galaxies? Or do you think that really we're mostly limited to Sagittarius A star and our galaxy?
It's a good question. Obviously, I want to get as many observations as I can because I'm a greedy astronomer. But there are a few limitations for how we can apply the data analysis that we've developed for this observation to other ones. This molecular cloud has very narrow iron K alpha lines. Other systems do show iron K alpha emission, but it might have a relativistically broadened line. And in that case, you wouldn't see the doublet. You couldn't constrain the redshift with as much precision because the line would be smeared out, blue shifted and red shifted. Like I said, there's an upcoming paper by our Japanese collaborators, Nobukawa et al., looking at a different molecular cloud in the galactic center. I'm really excited to compare those two measurements. And finally, the X-ray reflection model, because the brightness we see from these clouds depends on the external illuminating source, we do expect these clouds to change in brightness over a timescale of perhaps a decade or so, which sounds like a great reason to revisit these clouds in the future and make a great X-ray movie of them getting brighter or dimmer.
Lexi.
I have one more question. I'm Lexi Galt from the AAS. This time for Sumit. I'm not sure if this is outside of the scope of what you're doing, but I was curious if you could potentially use like resolved stellar populations and get star formation histories and connect the past star formation events to localized gas kinematics to try to see like, could there potentially have been supernovae that injected energy into the ISM?
Yeah, I think this is actually something that the FAT panchromatic Hubble Andromeda Treasury and the extension of that to the triangulum, I think it's triangulum extended region or fatter. So these people, I'm sorry, I didn't make the acronyms, but these people, one of the science cases is to, basically turn these star formation histories into supernova rates and then turn that into an estimate of how much energy you put in and then compare that with like the sizes of, cavities in these atomic and molecular gas maps. So right now, as I said, our maps are at about 50 parsec resolution. We're trying to get it down by like about a factor of 2 to a factor of 10. Once we do that, I think we're going to get very clear sizes of, cavities and stuff. And then this science is going to come in. There has been studies done like this before with lower resolution maps, but I think this will give us a lot more information.
That's super cool. Thank you.
All right. Any further questions? If not, we'll go ahead and wrap up a bit early. So thank you again to all of our presenters for their work. Thank you to their PIOs for preparing releases and helping prepare graphics and all of that. Thanks to all of you for being here. And we hope to see you back again tomorrow morning at 10:15. We will be hitting the session Asteroids, Low Mass Stars, and a Mystery from History.